Hi, welcome back to Power Electronics Lectures. In this part of this lecture, I will talk about the switch mode conversion. In power electronics, transistors and diodes operate as switches, either on or off, which is in contrary to linear electronics. Let's consider this transistor. Let's say that we have an IGBT transistor. Here we have the gate, the collector, and the emitter. Here we have the VGE, the gate emitter voltage, and the collector emitter voltage, VCE. And here we have the collector current. Let's draw the characteristic curve of this transistor, the collector emitter voltage versus the collector current. We know that when the current is increasing inside the transistor, what happens to the collector emitter voltage? We expect that the collector emitter voltage increasing as well. In the BJT transistor, we remember that we have the base. On the MOSFET, you'll find the drain and source and gate and so on. Anyway, so when the collector emitter voltage is increasing, or when the current inside the collector increasing, we expect that also the voltage across the transistor collector emitter will be increasing as well. In the previous time, we work in this linear region. But this is not the case in power electronic system. In power electronic system, we will work either in the saturation region or in the cutoff region. Okay? So we use the transistor as a switch, either on or off. We will never work in the linear region. When the signal on the gate will be 5 volt, which is a small signal compared to the power side, this means the transistor is on, and when the transistor is on means the current flows inside this transistor, so it will be as a short circuit. When the VGE is 0 volt, then the transistor will be considered off, and when the transistor is off, this means the transistor acts as an open circuit. The main feature of power electronics is that it achieves high efficiency because the on or off state of the switch should ideally draw zero power from the switch. So let's consider this switch when the switch in the on state, which means it's short circuit, and this is ideal switch. Let's say the switch will drop 0 volt when it's on, and the current will be any value. Let's say the current is I, which means it can be 5 ampere, 10 amperes, any values of the current. If you try to calculate the power, then the power will be 0 volt times the current, which is 0 watts. And this means that the losses when the switch is on is equal to 0. The power loss is 0. Let's have a look when the switch is off. You will find that when the switch is off, this means it's open circuit, open circuits, 0 currents, and we have a specific voltage. we have a specific voltage across this transistor or this switch. If you calculate the power, then the power will be the current times the voltage again. So it's zero current times any value, it will be 0 watts. Again, this is an ideal switch and also will drop 0 power losses when it's off. Let's consider this power converter, a simple power converter. Let's say we have a chopper, and this chopper has a capacitor on the input. We have a switch. This switch can be anything. It can be transistor, for example. And let's say this is connected to a resistor series to the switch, but we will take the voltage before this resistor. So let's say so the switch here on and off all the time, frequently, and the voltage will be taken V out just after the switch directly, and the Vn will be on the input, on the capacitor, and it will be a constant voltage, Vn, like a DC input, DC voltage. Let's see how the voltage on the output will look like. Let's draw the time again versus the V out. So when the switch is on, means the switch is short circuit, so the output voltage will be equal to the input voltage. And then this is when the switch is on. So the V out will be equal exactly to the Vn because the switch will be short circuit. So this is just the input voltage. When the switch is off, what happens at that moment? The current will be 0, and then the output voltage will be 0, nothing, because the output is not connected to any power source. So here we have no value in the output, it will be 0 volt. Okay? Again, when the switch is on, short circuit, then V out will be equal to Vn. When the switch is off, then V out is equal to 0, and so on. By this, we convert non-frequent DC voltage, Vn, into frequent waveform, V out, at high repetition. And this high repetition rate is called switching frequency. Let's calculate the average value of the output waveform. How can we calculate this? Just imagine that this volt, this Vn, is distributed to the switching time, to the T on plus T off. So here we have the input voltage over T on. The average simply can be taking this square and distribute this value to the whole period of time, T on plus T off. So the blue area here represents the average voltage. If we try to calculate this average voltage, how can we calculate this value? We can say that T on, the on time, over the whole period of time, T on plus T off, times the input voltage Vn. Okay, so this is the average value of the output voltage. So here the whole period of time, T on plus T off, we call this the switching time. And T on over the switching time, this is all the time must be between 0 and 1. Cannot be more than 1, it cannot be less than 0, or even it cannot be 0 or 1. Otherwise, we'll not be able to switch. And that's what we call the duty cycle, delta. T on over T on plus T off is delta. And usually we use this term, the TS, the switching time. This is 1 over the switching frequency. I hope that you enjoyed this lecture. Next lecture we will talk about a brief overview on power semiconductor devices, the power devices, these transistors and other devices that we use in power electronic systems, and we will talk about their key applications. And see you next time.